Okay, good morning everyone, and thanks for joining today's webinar. We will get started on time in 3 minutes. Good morning everyone, and thanks for joining us for today's webinar entitled Phosphorus Stratification, Dealing with the Invisible P-Specter on Cropland. It's not a myth. My name is Anna Goodjohnsdottir, and I'm the team member at the Partnership for Ag Resource Management who is hosting the webinar this morning. We are joined today by my colleague Dr. Thomas Green, President and co-founder of the IPM Institute, who will provide a brief introduction. I'm also pleased to welcome our guest speakers. First, we'll hear from Dr. Mark Williams, Agricultural Engineer for the USDA-ARS National Soil Erosion Research Lab. Second, we will hear from Dr. Peter Kleinman, Research Leader and Soil Scientist for the USDA-ARS Pasture Systems and Watershed Management Research Unit. At the end of their presentations, we will use the remaining time for Q&A. Before we begin, I want to share some brief logistics. You will remain muted as an audience member during the presentations, but please make use of the question box on your screen to type questions for the speakers, and please indicate if the question is for Peter or Mark. I will moderate the questions at the end of the presentation. This webinar is being recorded and will be available later on partnershipfarm.org. By attending the webinar today, you will be eligible for 1.5 CCA continuing education units, 1 for nutrient management and 0.5 for soil and water management. You must be present for the entire hour webinar to receive those points. If you are watching this webinar live, you will receive an email by the end of the day with the webinar recording and a link to submit the survey evaluations. A link and pop-up question will be provided at the end of this webinar to submit CCA credentials to earn points. If you are watching this on demand at a later date, please be sure to watch through the Citrix platform and not YouTube to receive credit. A link to register on Citrix will be provided in the text below the YouTube video recording, or it will be emailed to you if you are already registered for this webinar. You are provided instructions at the end of this presentation to submit your credentials. And now, with those logistics taken care of, I will turn it over to Dr. Thomas Green.
Thanks so much, Anna. Thanks everyone for joining us today. It looks like we've got over 230 people, which is a great turnout. So the Partnership for Ag Resource Management is a project of the nonprofit IPM Institute, along with our many other projects in agriculture and communities. Each of our projects is focused on using the power of the marketplace to improve sustainability. We're a team of 24 currently, working to increase adoption of best practices and improve outcomes in health, environment, and economics, all key elements of sustainability. You may have read one or more of the IPM articles that we write regularly for Crops and Soils magazine. We also work with pest control companies, hospitals, schools, and other facilities and communities, and with food companies and farmers around the world to improve practices and communicate those benefits to buyers and the public. Our goal with the Partnership for Ag Resource Management is to identify revenue opportunities for ag retailers that also help keep our valuable ag resources on cropland, help to promote those products and services, and track and report sales and estimated reductions in losses of nutrients and other inputs as a result of those products and services. And we'll talk about some examples in a moment. So as we all know, we face some real challenges in the Great Lakes and also the Mississippi River, Chesapeake Bay, and other watersheds. Nutrients and soil we need for our crops are leaving cropland and ending up in our rivers, lakes, and streams. These two photos show what happens when too much phosphorus gets into the water, feeding blooms of algae which close beaches to swimming, make fishing a challenge, and have also shut down public water supplies. The graph on the left shows NOAA annual data on algal bloom severity since 2002 in Lake Erie. After phosphorus loadings declined sharply in the mid-'80s with the advent of reduced tillage, they've increased. And as a result, we've experienced more frequent and severe algal blooms. 2015 was a record. It exceeded the prior 2011 record. 2016 was at 3.2, lower than the 5.5 predicted. And remains to be seen what this next year will bring. Of course, it's very weather dependent. And there are multiple sources of phosphorus, but we know that the phosphorus causing the blooms is primarily coming from cropland because of the timing of the loading. They spike during snowmelt and rain events in winter and early spring following fall applications. The increase has been in dissolved phosphorus rather than phosphorus attached to soil particles. And along with that increase, Heidelberg University and others have documented a concentration of phosphorus in the top layer of soil, which is the topic of our webinar today. After years of surface applications and rotational no-till systems, they've resulted in saturation of the soil with phosphorus and an inability to hold more phosphorus. As a consequence, we see the increased runoff plus movement down through macropores in and out of tile drain systems. Next slide. Ag retailers have valuable products and services which can heat phosphorus on cropland and out of waterways. Here's a list of some of those, along with some very rough average reductions in losses based on published studies. There's lots of variability in the published numbers based on soil type, slope, proximity to surface water, and other factors, but these rough averages give us a sense of where we can likely make a difference. Cover crops, soil testing, grid or zone sampling, and variable rate application, custom application are all revenue generating opportunities for ag retailers that also reduce phosphorus losses. We can also let farmers know when a broadcast application has been made so they can get that application covered. We can avoid application before a heavy rain event and abide by setbacks, and let farmers know when we see an issue that needs attention, such as a tile blowout. And of course, applying only enough phosphorus for the following crop rather than the next several crops in the rotation can also help reduce losses. So today we'll hear from experts about strategies to manage phosphorus, particularly that accumulation of phosphorus that occurs at the top of the soil profile. So next slide. Ag retailers are making a difference. For example, our annual survey shows big increases in variable rate phosphorus application across the Great Lakes Basin. In 2015, we secured funding for ag retailers to offer a discount on variable rate to farmers in the Sandusky River watershed who had not used it before. And we had 13 retailers and 95 growers participate. We've expanded that program to 3 additional watersheds in northwestern Ohio this year. So using the published estimates that we showed on the prior slide, the acres of variable rate here alone represent 1.1 million pounds of phosphorus that's no longer leaving cropland due to the application of variable rate. So we need to track and report the improvements we're making so that regulators and the public are aware of these voluntary efforts using the power of the marketplace to drive improvements. So you'll hear more from Anna about some additional tools and resources we have for your use, as well as our ag retailer survey that generated these numbers here that you're welcome to participate in. And so with that, I will turn the mic back to Anna.
Thanks, Tom. As Tom mentioned, we do have some free resources available on our website at partnershipfarm.org. On the left, you can see the front page of our agronomist handbook that is available free for download. On the right, you can see the front and back of our phosphorus loss reduction wallet card, which can be ordered for free on our website as well. These serve as a great conversation starter with your growers. Lots of people order them and take them to their various meetings. To date, we have distributed 19,735 wallet cards. I also have a couple of PARM announcements. As Tom mentioned, our 2016 Ag Retailer Survey is out, and a link to participate will be included in the follow-up emails. Our goal is to track ag retail sales of products and services that keep ag inputs on cropland and out of the Great Lakes. Please note that this survey is just for ag retailers within the Great Lakes Basin. Our next webinar is February 22nd, and we will be covering the topic of cover crop termination, so mark your calendars for that. And last, we invite you to follow us on Facebook and Twitter for PARM updates and industry news after the webinar. After the webinar would be perfect time to look us up from your computer or mobile device. Now we'll hear from Dr. Mark Williams, agricultural engineer at the USDA-ARS National Soil Erosion Research Lab.
Can everyone hear me all right? All right, so this morning we're going to be talking about phosphorus losses and surface runoff and tile drainage in the western Lake Erie Basin. A lot of this research has been conducted in both Ohio and Indiana over the past few years, and today I'm just going to give an overview of some of those results. So we all know why we're here and what the problem is. It's looking at phosphorus inputs into Lake Erie and the re-eutrophication of Lake Erie. Lake Erie was once a conservation success, but it has in recent years kind of been trending the opposite direction, where we've seen more nutrients, more phosphorus entering the lake than we had been previously, and these have been resulting in more severe algal blooms over the past decade or so. So Heidelberg University, their tributary monitoring program, has been monitoring these phosphorus loads since the early 1970s, and they've shown that over the past 20 years, dissolved phosphorus loads in both the Sandusky River and the Maumee River have been increasing pretty substantially. So the billion-dollar question is what is causing these increased dissolved phosphorus loads to Lake Erie? In 2015, Doug Smith, another USDA colleague, put together a list of 25 different theories that could be contributing to phosphorus losses in the western Lake Erie Basin. And those Different things range from climate change, commodity prices, zebra mussels, tile drainage, stratification, which is the topic of our presentations today. But there are a lot of different theories that are out there of what's causing the problem. But the most important thing to remember from this long list of potential sources of the problem is that it's not just one of these individually that are contributing to the problem. It's multiple factors and a very complex landscape that are resulting in this. So if you take that list of 25 different theories of what's causing the phosphorus increases in Lake Erie, you can really break them down into two categories. That's the most simplest form if you just take a step back and look at the big picture. And those are phosphorus sources on the landscape. So in order for phosphorus to get into Lake Erie, there has to be a source of phosphorus somewhere. And also there has to be a way for that phosphorus to be transported from the field where it is applied into Lake Erie. So these are two of the main components that are controlling phosphorus loss. So if we look at a broad perspective across the western Lake Erie Basin, specifically in the Maumee watershed, this is a study that looked at essentially the inputs and outputs of phosphorus into the Maumee watershed since the 1970s. And what this study showed was that since the 1970s, we've been accumulating phosphorus in our field, and a pretty substantial amount of phosphorus. While over the last 10 or 15 years or so, our inputs and outputs have been relatively in balance, close to a nutrient balance of 0, we've still had all this accumulated phosphorus that has built up prior to that still remains in our system that could potentially be lost to Lake Erie. And when we think about transport, the western Lake Erie Basin used to be a large wetland. And this is a diagram of the St. Joe River watershed in northeastern Indiana. And the red areas are closed depressions. So historically, these would have been small landscapes small wetlands that would have dotted the landscape. But then with settlement and increasing in farming and other things, we've increased the ability of water to be transported from these closed depressions. So the dark blue line in the middle would be a ditch, and then the lighter, thinner blue lines are tile mains. And you can see a lot of these tile mains connect these otherwise disconnected landscape features. So we're allowing water to be transported from these to the ditch, to Lake Erie, much faster than we would have been historically. So just kind of what does that mean? So if you think that of this red box here on the screen, and then you have a ditch or a stream network relatively far away, that water and phosphorus, without any hydrologic modification, could have taken 20 to 50 years potentially to reach the stream through groundwater infiltration and recharge. And then throughout history, we went and we installed drainage ditches across a lot of our landscapes. So now our field, it may only take 1 to 5 years for that water and nutrients to get to the ditch and then to the stream. And then with more and more pattern tile drainage being installed, we are allowing water and phosphorus to move even quicker now than before. So that just means that our management of individual fields that would have been disconnected previously is really important for phosphorus management. So we get a lot of questions about what are the magnitude of phosphorus concentrations and losses in tile drained fields. And today I'm going to give a little overview of some of the research that I've done with Dr. Kevin King with the USDA in Columbus, Ohio. And he has developed an extensive edge of field monitoring network. And you can see here on this graph, the black dots represent all the different edge of field sites that are throughout Ohio that I'll be summarizing today. So when we think about the transport aspect, how much water is leaving the field, here shown on the y-axis, we have the depth of water leaving the field, or it could be also precipitation, and then months. So these are average values for all of the edge of field sites, so over 40 monitored fields that we've been collecting data from. So what you can see from this is that the hashed bars are subsurface drainage and the white bars are surface runoff. So the majority of the water leaving the field during a given year is through the tile drains, not through surface runoff. And just average across the whole year, 79% of water leaving tile drained fields is through the tile itself, not through surface runoff. And while this can be a good thing for phosphorus concentration, phosphorus loading to the tiles can be more problematic. So looking at just a big picture view again of phosphorus concentrations across all of these sites, and we have this broken down by season. And this is the mean flow-weighted concentration of both dissolved phosphorus and total phosphorus. And again, the subsurface tiles are the hashed box plots, whereas the white ones are for surface runoff. And you notice two things here. One, the boxes for surface runoff are generally higher than those from the subsurface tile drains for both dissolved P and total P. If we look at the concentrations for dissolved phosphorus at an annual level, so from all of our sites, we see that on average, dissolved phosphorus concentrations in tile drains are 0.08 milligrams per liter, and for surface runoff, it is 0.21 milligrams per liter. Again, this goes back to potentially phosphorus stratification, where there's more phosphorus on the shallow surface layers. The concentrations in runoff are going to be higher than what's infiltrating through the soil. But when we compare this to recommended concentration reductions, we still see that both tile and surface runoff are above these critical thresholds. And that means we still have work to do in order to reduce these concentrations to prevent algal blooms in Lake Erie. And similarly for total phosphorus, again, we see that average annual concentrations for total phosphorus are 0.19 milligrams per liter, and for surface runoff are 0.43. So for this, actually, our tile drain total phosphorus concentrations are lower than the threshold for what's coming out of the tile, but still almost double in surface runoff. So now looking at phosphorus loads, so the combination of both concentration and water transport. And here we just have dissolved phosphorus load in kilograms per hectare, which is essentially pounds per acre per year. And the black part of the bars represents the loading from tile drains, and the white part represents the loading from surface runoff. And these are, the letters represent different field sites that we have monitored. So again, what you'll see is that a large portion of these bars are from tile drainage, and only a small proportion of the bars are from surface runoff. So to meet, for these sites that we've been monitoring, which we feel are pretty representative of the agricultural practices that are being implemented throughout the western Lake Erie Basin, the loading targets are being met in 50% of the site years. So that means 50% of all the sites in all the years that we've monitored have met the dissolved phosphorus loading targets. And on average, the tile drains accounted for 65% of the total field dissolved phosphorus load. So how do these loadings and concentrations relate to the phosphorus levels in the soil? So our soil test phosphorus levels. And today I'm going to be comparing the loads to Mehlich 3 soil test levels. And we've broken this down into two time periods. The spring, which represents March through July, and then annually, so an entire year. And the reason we did this is because the loadings we know the loadings to Lake Erie are most important during the spring. That's when a lot of the phosphorus that's transported to the lake leads to the algal bloom later in the summer. So while these two graphs show, again, dissolved phosphorus load versus Mehlich 3 soil test, and the open or white symbols represent years where no phosphorus was applied to the field, and the other black symbols represent when there was a phosphorus application. And we have this in a log scale, so we can show the variability in the data. But what we found was that when we look at the relationship between soil test level and load, we see that in order to meet the spring loading goal of 0.11 kilograms of dissolved phosphorus per hectare, which is recommended for Lake Erie, we would need a soil test phosphorus level of -12 with no phosphorus application. And you may ask, well, how is that possible? How do we have a soil test level of -12? And that's negative values obviously aren't possible, but that just means that our soil test is going to be very hard to meet that loading threshold in the spring without other water management practices like drainage water management and things like that to meet those goals. But on an annual level, so not necessarily so focused on the spring, in order to meet our annual loading thresholds, we need to have our soil test less than 28 milligrams per liter. So this is kind of saying for fields with soil test levels, and this is 0 to 8 inch depth, for soils with less than 28 milligrams per kilogram of soil test phosphorus, we'd be more likely to meet the threshold than those fields with greater than 28 milligrams per liter phosphorus. So that comes back to one of our 4R principles, applying the right rate. So this is a global study where they look at it by continent, so it's not really necessarily specifically practical for the Western Lake Erie Basin, but it gives us an idea of applying the right rate. So they broke it down by region, essentially by continent, and they looked at, well, what if 20% in this first column, what if 20% of the soil phosphorus that we have in our soils already was available to crop? How many years of phosphorus do we have in our soil to supply our crop needs? And then again in the next column over, what if 50% of that phosphorus in the soil was available for crops? So for North America, we see that ranges from 7 to 18 years of phosphorus that's already in our soils that is potentially available, and we wouldn't need to fertilize our fields for that many years. And while this is highly site-specific and it's kind of hard to look at soils across North America and compare them just to what's in the Western Lake Erie Basin, we need to remember that there is phosphorus in our soils that does become available over time. And we need to account for that phosphorus when we are applying our fertilizer. So not over-applying our phosphorus because there is some in that soil that's already useful and can be taken up by crops. And now moving on to the stratification. We know that most soils in the Western Lake Erie Basin are stratified. This is the study by Heidelberg University in the Sandusky watershed where they looked at environmental soil test phosphorus. So that was in the top inch of the soil profile versus the agronomic soil test level, which was 0 to 8 inches. And they also looked at Malik 3. And most of the dots on this graph are above the solid red line. That means there's more phosphorus in the top inch of the soil relative to the soil test of the entire 0 to 8 inch profile. And this stratification may exacerbate our phosphorus losses. So this is again some data from our edge of field sites where these green bars are soil test phosphorus by depth for the site. So we can see that even in our edge of field sites, we do have phosphorus stratification, whereby our 0 to 1 concentrations are higher than each of the depth increments as we go down through the profile. But on the opposite trend, we see these gray bars, which do the exact opposite. The green ones go down, the gray ones go up. And the gray bars represent the soil phosphorus absorption capacity. Essentially, are our soils functioning as a source of phosphorus or a sink of phosphorus? And this takes into account the iron and aluminum that's in our soil. So with our soil test levels of around 60 parts per million in the top 0 to 1 inch, this values less than 0 would indicate that our soils are a source. So most of our phosphorus absorption capacity has been already reached in the 0 to 1 inch, and our capacity increases with depth. So that means this phosphorus that's on the surface, even up to almost 2 inches depth, can possibly be a source of phosphorus that's leaching phosphorus. It can't bind anymore, even at a soil test levels between 50 and 60 parts per million. So for phosphorus stratification, what kind of implications can this have for phosphorus transport at the field scale? And in this study, we weren't specifically looking at phosphorus stratification, but it's a good example of what stratification could do. And we were looking at studying preferential flow. So we had two edge of field sites that we were looking at. They had been in long-term no-till for 30-plus years before we did this study. And the year that we did this study, the farmer on May 6th applied approximately 175 pounds per acre of MAP to both of these fields, and then 2 days later he dished in the fertilizer on the one field, but the other field remained in no-till. So we were able to see how phosphorus at the surface can influence tile losses. And this is just a picture of the phosphorus on the soil surface relative to some of the cracking we see in our soils in the western Lake Erie Basin. So when we have, whether it's from fertilizer, like is shown here, or if you can imagine that there's this large amount of phosphorus stored right in the first top into the soil, that when we have a rainfall event, we get runoff, this water can flow across the surface, collect that phosphorus, and right down into the cracks and into the tile stream. So this is looking at the dissolved phosphorus dynamics before fertilizer and tillage. So this is under essentially baseline conditions, and both fields were managed the same for a long period of time. We see here the blue line is tiled flow, and then the red lines are phosphorus concentrations. So we see that phosphorus concentrations were still above the critical threshold at 0.08 milligrams per liter, but they were still relatively low. We didn't see much of a response during the storm event. And as a result, the loading from these fields was both the same, which we would expect because they were managed the same. We had a very small load for this event of only 12.6 grams per hectare, so pretty small. So let's look after the fertilizer and tillage. So this graph on the left is for the tilled field, and the graph on the right is for the no-till field, where we would have phosphorus, soluble phosphorus at the surface. This is showing an example of what either stratification or broadcast fertilizer can do for tile concentrations. So after the fertilizer, we saw a response in the phosphorus concentration with an average concentration of 0.58 milligrams per liter. But in the no-till field on the right, we saw this huge increase in concentrations, nearly up to 5 milligrams per liter. Remember, our concentration threshold is 0.05, so this is orders of magnitude greater. And our average concentrations were 2.12 milligrams per liter. When we translate that into load, you can see there's also a difference in discharge between the tilled and no-till field. We see a large increase in phosphorus loading from the no-till field relative to the field where the fertilizer was incorporated via tillage. And while there are a lot of benefits to no-till, I think it's important that we don't just go out and start tilling all our fields, because that is how we reduced our total phosphorus loads to Lake Erie. But there are unintended consequences of no-till that may increase dissolved phosphorus loading through stratification and broadcast fertilizer application. So we've done a recent follow-up study on this, looking at injecting our fertilizer, dry fertilizers, versus tilling them in. And what we found was that the injection and tillage both result in the same reduction of phosphorus losses relative to broadcast application. So we think there are ways that we can have the benefits of no-till to reduce sediment and particulate phosphorus and surface runoff, but at the same time get our phosphorus down into the soil profile through some sort of injection, and that will not only reduce stratification but prevent that soluble phosphorus from just sitting on the surface. So in summary, phosphorus concentrations from fields are often above critical thresholds that have been set for the Western Lake Erie Basin. And there's a lot of phosphorus that's already in our soils that should be accounted for when we're applying fertilizer. We have to think of this legacy P and how we can utilize it. And that comes back to our 4R principle of applying the right fertilizer rate. And with that, this legacy phosphorus that is built up has mostly been in the surface layer. And this stratification can exacerbate phosphorus losses in these landscapes. So with that, fertilizer placement is important for decreasing stratification and phosphorus losses from field. This comes back to the 4R principle of right placement. And that's all I have for my presentation today. I look forward to any questions that you may have. Here's just my contact information if you would like to reach me outside of the presentation. Thank you.
Okay. Thank you, Pete. Or no, thank you, Mark. Next we'll hear from Dr. Peter Kleinman. Peter is a research leader and soil scientist for the USDA-ARS Pasture Systems and Watershed Management Research Unit.
All right, thank you, Anna, and thank you, IPM Institute, for inviting me today. Can you hear me and can you see my slides? I'm going to just transfer over here.
Yes, we can hear you.
Okay.
And your slides are coming up.
I have them. So there should be my title slide, phosphorus build. Okay, I'm going to probably hit a lot of the same points that Mark Williams discussed, but I'm going to take a little different tact on this. And it occurred to me in looking at Mark's presentation and even in developing mine, our focus, and I thought our charge was basically looking at soil phosphorus stratification, but it's almost impossible to separate that from the issue of leaving fertilizer on the surface. Now, when we address this from a management standpoint, we try to kind of parse them out, treat them separately. So soil phosphorus stratification is something that is a long-term issue. It actually accounts for what we call the legacy phosphorus, whereas when we apply fertilizers and manures to the surface of the soil and they wash off, that's decidedly a short-term management issue, and one contributes to the other. I'm going to talk more about the soil end of things in my presentation. So the presentation today is going to address, let me try to move some things out of the way so that it's not distracting to you. Kind of three general areas. I'm going to talk a little bit about phosphorus fertility, and that you know, some of the environmental issues that we see today are actually as a result of successful agronomic management and overcoming things that are in our systems, natural buffers that are in our systems that would prevent phosphorus from being available to our crops. I'm going to get into water quality, but Mark did an excellent job of basically addressing that. Probably bring a little more in terms of focusing on soil phosphorus stratification. And at the end, we'll cover some of the same management issues. I think a priority one being, and particularly for this group, soil testing at the fore. And so the kind of soil testing that we need is different than the soil testing that we generally do for agronomic purposes, if we even do that. So we'll get into that as we go along. Okay, so this next slide then is a map of the world, and you have to look at our production issues from the standpoint of agricultural development. And with this map, what you see are red colors indicating very high binding potential or phosphorus sorption capacity, and then the lighter colors, the yellows and the green, being lesser binding potential. And many of the soils of the world have tremendous phosphorus retention or binding potential. And so we focus our agronomic management on trying to reduce that potential so that when we apply a fertilizer to a soil, it stays available for the crop. But it can have the unintended consequence of also making that phosphorus more soluble in runoff water as well. So this is, there are two different graphics right here. One of them here on the lower left shows plant root and shows the fact that phosphorus from an agronomic potential standpoint, from the standpoint of growing crops, is a relatively immobile element. In fact, our crop roots more or less have to grow to the phosphorus in the soil in order to retrieve it. It moves only just a few millimeters to around the rhizosphere, whereas other fertilizer elements are much more mobile and can diffuse into the root zone. So phosphorus really sticks around. Therefore, where the phosphorus is in the soil is really important. This diagram right here shows a plant root growing down, which is what they do. And so really we're looking at accessing phosphorus through the plant roots where the roots are growing. So on the right-hand side is a diagram actually that comes from a lab in which you see what we're trying to do when we manage phosphorus in soil. So this graphic shows on one, I have a sense of the screen here, shows phosphorus in the soil solution relative to phosphorus that's sitting bound to soil particles, so in the solid phase. And what it shows is this is probably a native soil right here. In fact, this is a native soil from Pennsylvania, and most of the phosphorus in that native soil is bound by the soil, whereas very little stays in the soil solution, the soil water, where the crop can get to it. Now, if we use nutrient management, things like liming, things like adding phosphorus to the soil to help to overcome and saturate the binding potential, we end up with a soil like this, in which of the amount of phosphorus in the soil, more of it stays in solution than is bound by the crop. So this is very, very important. This type of soil right here, we can use phosphorus fertilizer much more efficiently. When we add an incremental amount of phosphorus to it, much less is bound relative to what stays in solution. And that is essentially our approach. It's kind of a crude approach, but it's our approach to fertilizing soils. There's a lot of uncertainty that's involved, as I think all of you know, in generating fertilizer recommendations, and many of our fertilizer recommendations are relatively old. So some of the more recent ones are ones that my colleague Antonio Malorino generated. You can see this is a publication from 2003. This is just not a sexy subject when it comes to applied science. And you can also see that we're looking at kind of clouds of data and then parsing out thresholds based upon this. So this graph here relates soil phosphorus, melic-3 phosphorus, to the relative corn yield. And from that graph, you can see then you have various thresholds that take you from low phosphorus availability to optimal phosphorus availability to high to very high. And so there's a lot of noise in there for making those types of distinctions, and that's important to keep in mind. So this was actually done two different ways. Same study with, here's using one method for measuring the phosphorus that's extracted by the soil test, and then here's another one. This is using a spectrophotometer that's called an ICP, and in this one it's much more efficient at measuring the phosphorus in the test, and therefore the thresholds are higher than with the other one. So it's important when you're looking at soil tests to understand that there's uncertainty. Historically, we've used that uncertainty to basically add phosphorus to our recommendations. Now with environmental concerns, we really need to think about having less phosphorus rather than more phosphorus in the system because of the potential for offside consequences. So this slide right here shows that crops have different demands for nutrients, and so we grow crops in rotations, and so when you're managing and you're thinking about the 4 R's and going at the right rate, you're not just you've got to think within your rotation and at the specific crops that you have. They all have different demands in terms of what their critical thresholds are for phosphorus requirement. Now let's start to get to the vertical stratification. So we are pretty crude in many ways in how we manage phosphorus. We have generally tried to reduce the soil's ability to bind that phosphorus so that we can keep it available to the crop. We also tend to apply phosphorus to the surface because getting it underground can be difficult, and we have technologies, but they're not necessarily widely adopted. So here's a study that a colleague of ours, Andrew Sharpley, did in Oklahoma, where they added poultry litter as a phosphorus fertilizer to the surface of soils that were in grass. And over 10 years, you can see the differences in the amount of phosphorus that's at the surface related to the different rates of application. So Dr. Williams mentioned the kilograms per hectare is roughly pounds per acre. So they had no manure, 50 pounds per acre, 100 pounds per acre, and you can see dramatic differences in the soil test phosphorus, and those differences are greatest at the soil surface. And in fact, they disappear as we get down in depth to about a foot in depth. So what we know from our experimental research and from research in the field is that phosphorus at the soil surface tends to be the control on phosphorus that's lost in surface runoff, and also it can be a major control on phosphorus that's lost in tile drainage as well. And so we call that the effective depth of interaction. That is the zone where runoff waters interact and retrieve most of the phosphorus that they then take off-site if they move off-site. And it's particularly true for overland flow, for surface runoff, but it also applies to subsurface flow or leaching to tile drains. So this slide here actually is obtained from the same study that Dr. Williams showed, Dave Baker et al., and I obtained these data from his colleague, Laura Johnson. It is from the Western Lake Erie Basin, again with the background being that there's a concern that no-till might be contributing to some of the trends that you see in terms of dissolved phosphorus runoff to Lake Erie. And what they did was they sampled soils either using a traditional sampling depth of 8 inches or by actually stratifying their sampling. And so one way that you can look at it is not just as a soil test, but also kind of as an example of mixing. They're mixing these different depths that they have. For 8 inches, they're mixing everything in there. And so you can think of that as a very efficient form of tillage. With these other ones, they're performing tillage on the surface or either in the subsurface. And what you see are very different averages in terms of the soil test. So when you take an 8-inch sample across the soils that they sampled, you had an average of 36 milligrams per kilogram or parts per million. When you took a 2-inch sample, you had an average of 55 and then 28. And then when you broke it up even more finely to 1-inch samples at the surface, you saw you had peak concentrations averaging 60 milligrams per kilogram. This is in a watershed that has primarily rotational no-till, so it's not permanent no-till. That is periodically the soils in this watershed are plowed, and so mixing does occur. And continuous no-till is actually kind of the minority land use. And so what we see, and we see this in research that we do all over, is that phosphorus can accumulate on the surface very, very quickly over just a couple of years. And the differences in what we see in a soil test can be quite profound. And I think this study just illustrates that beautifully. So 36 for an 8-inch sample, whereas if you did a quote-unquote environmental sample or a surface sample, 55. And I think this is the reason why, you as retailers and people who are really concerned about vertical stratification as a factor need to be considering periodically sampling in a way that gives them the kind of results that you see here. Let's look at that now in terms of from an agronomic standpoint. And so Doug Smith, who was mentioned earlier, went out in the field in Indiana and sampled a number of soils and then related that to the yields that he got back from farmers with whom he was working. And what he found was when he took that shallow sample, the 0 to 2 inch sample, and he tried to relate it to corn yield, it in fact was quite poor. Okay, so it's just not something that where you would just go and take a 2 inch sample for agronomic purposes. But then when he looked at the phosphorus that was at depth, he actually had quite a good relationship right there. You start to see this relationship between phosphorus and the corn yield in bushels per acre. And these are the same soils. It's just either a 2 inch sample or a 2 to 8 inch sample. And this should drive home the fact that crop roots grow down, and where crops are getting their fertilizer, phosphorus, where they're getting the phosphorus that they use is at depth. It's not on the surface. And so what we're putting on the surface really is not of great use to the crop itself. Here are data that come from Mark and from Kevin King to basically drive home the subsurface side of the equation. They looked early on in the study that Mark showed you at the relationship between the concentration of dissolved phosphorus and tile drainage from the fields that are monitoring and the concentration in the upper 2 inches of soil. This is just basically raw data with flow-weighted mean concentrations from the first year or so of their study, and they found the relationship that you see before you right there. So in tile drainage, that relationship between what's sitting on the surface and what comes out can be found. And if you start to think about it in terms of the tri-state recommendations, you need about 50 parts per million or milligrams per kilogram melic-3 phosphorus to grow a crop. So where you're seeing very high concentrations tend to be at higher soil test phosphorus levels, and that came out in Mark's talk as well. And so we call that, those higher levels, legacy phosphorus. They're a product not of this year's application, but of historical application of phosphorus to those soils. So let's look a little bit at some studies that get at the vertical stratification and what it can mean in terms of environmental impact. Here, some data that come from Andrew Sharpley when he was in Oklahoma from some large experimental fields. There they monitored the runoff that came from these fields. The fields were in conventional wheat production with tillage. There was some moldboard, but there was also chisel plowing that was going on there. And the two graphics that you see in front of you are the total amount of phosphorus that came out, the concentrations that came out in surface runoff, and then the dissolved phosphorus that came out. So dissolved phosphorus is just a fraction of total phosphorus. The difference basically is particulate phosphorus or sediment phosphorus. And so they did what we call a paired watershed study, where they basically monitored two watersheds, and then on one of them, after they convinced themselves it was acting like the other one, they imposed a treatment. And that treatment was to go to no-till. And so what you see with this graphic right here is that in the second watershed, after they imposed no-till, they had about a 95% reduction in erosion, tremendous conservation benefit. This is what Mark was talking about, the historical gains in Western Lake Erie with the original approach to dealing with Lake Erie eutrophication. And so the total concentrations of phosphorus in runoff dropped dramatically in association with that. And that's all because they prevented the sediment-bound phosphorus from leaving the field. But when you looked at the dissolved phosphorus, and note that these are on different scales. So we're going up to 6 milligrams per liter for total phosphorus. For dissolved, it's 1. There's less phosphorus leaving the field, but the dissolved phosphorus concentrations go up after they impose no-till. And that is because they're accumulating phosphorus very quickly on the soil surface, and that phosphorus is in what we call the effective depth of interaction and is available to the runoff water. And so this is the conservation paradox, is what we've come to call that, where we can fix one problem, but we create another one. It's a lesser problem in terms of the magnitude that comes off, but it is a very problematic one because it's really hard for us to manage. I want to really kind of hit this home with one example from Lake Erie that Mark didn't present. This comes from the folks at Heidelberg University who, in combination with some partners, took advantage of an EPA grant where they targeted 2 different watersheds and they implemented a variety of things, cover crops, winter wheat, even some no-till, to try to address phosphorus loss in the flat landscapes. These are these tile drain landscapes that they have right there. What they found was that when they implemented them in Honey Creek and Rock Creek. They basically kept that as a control. That when they looked at the sediment-bound phosphorus in these flat landscapes, that over time the losses basically didn't really change after they implemented these best management practices, the cover crops and the no-till. And so you see that with the sediment-bound phosphorus. So the yellow line here is when they implemented it. But when you go over and you look at dissolved phosphorus, what you see is that in Honey Creek, where they implemented the cover crops and the no-till, you started to see a separation, and this was a statistically significant separation in terms of the dissolved phosphorus losses from Honey Creek watershed relative to Rock Creek watershed. And the principal hypotheses there are that dissolved phosphorus came from the vegetation, actually the vegetation cooking on the soil surface, so lysing in the winter, the breakdown, the decomposition of the cover crop cells, and them washing off, and as well as to stratification right there. So this is after implementing some BMPs that are really they're soil conservation focused ones and not dissolved phosphorus BMPs. So I'm going to start to get into management now. Mark talked about basically making sure you applied at the right rate, and you were thinking about this year's crop and not long-term and applying for several years. And you can get extreme cases of soil phosphorus buildup. I work on the Delmarva Peninsula of Maryland, and there you have a lot of historical application of poultry litter. That it doesn't happen the same way anymore, but in the past a lot of litter went down on soils and added a lot of phosphorus to it. So we implemented what we call a mining study or a drawdown study, where we stopped applying fertilizers and we just tried to harvest and remove the phosphorus in the soil through a corn-soybean rotation. And what you see basically here is that starting at very, very high levels, so starting at about 450 parts per million, that after a decade, we really hadn't changed this soil test phosphorus. A lot of phosphorus is sitting in reserve in the soil and was still getting kind of pumped into the available phosphorus fraction, and actually liming helped to exacerbate that problem. So other studies have looked at this also, and what you see generally is the higher your starting point in terms of legacy phosphorus or soil phosphorus, the longer it takes to draw that phosphorus down to agronomic threshold level. So 50 again for malic 3P is roughly the threshold. That's a threshold that most states use. And you can see that the higher your starting point, the longer it takes to mine that phosphorus down. It's a very, very slow kind of a process for drawing it down. And you're not necessarily drawing it down at the soil surface. These were all studies in which they looked at 6-inch or 8-inch samples. One thing that I have advocated people try periodically, and it gets a lot of pushback from the conservation community, is if you're tracking vertical stratification and you know you have a lot of phosphorus in your soil and a lot of phosphorus at the soil surface, that you consider bringing up some of that binding potential from the subsoil by a periodic or one-time tillage event, where really what you're doing is you're trying to bring up soil from below and mix thoroughly. So this is a one-time event. There's a great concern that the impact on soil health, the impact on erosion will basically undo any benefits you get from dissolved phosphorus, and that has to be kept in mind. This is by no means an advocacy for just wanton tillage, but there's a great study that Andrew Sharpley conducted. It was done under highly controlled conditions in which he basically did rain simulations on two soils that one was untilled, so essentially kind of starting as a no-till soil. The other one, he imposed tillage, and you can see that the concentrations from the untilled soil that was starting at about almost 500 milligrams per kilogram phosphorus were on the order of about 8 parts per million or milligrams per liter total phosphorus in runoff. When he imposed tillage on the other soil so that he mixed in the subsoil, he brought down the concentration of phosphorus in that soil to 136 milligrams per kilogram. This is still almost 3 times more than what the crop needs to grow, but it's dramatically less. It's less than half of what his starting point was right there. He did the rain simulations, and what he found was in those first rain simulation events after tillage, he had a spike in phosphorus loss that was primarily associated with sediment washing off. And then over time, though, as he continued on and the soil stabilized, the concentrations that he got in runoff were much, much less in the tilled soil than in the untilled soil. And that's because he basically diluted the phosphorus that was sitting on the soil surface, that stratified phosphorus. He brought it down right there. And so the longer term benefit then is really one aimed at dissolved phosphorus here, understanding that you're going to have a short-term cost, but in the longer term, you can actually reduce that dissolved phosphorus through something like tillage. And this has to be in the toolbox that folks have as they're thinking about vertical stratification. Here's a study that we did where it was with dairy manure, and we used tillage again. Prior to dairy manure, we were looking at phosphorus leaching through soils, which is kind of the main concern in the Great Lakes region or in the lake plain areas. You can see what we had before we applied manure. And then we applied manure either by broadcasting and leaving on the soil surface or by broadcasting it and tilling it in. And by broadcasting and tilling in, what we did was we mixed the manure thoroughly with the soil where it can actually react better with the soil. We also conceivably plugged some of the macropores, some of those cracks that you saw from Mark Williams' photo, also earthworm burrows, things like that, and prevented them from serving as kind of highways of leachate route to the bottom. And so when you look at the differences with the broadcast manure, when you applied manure, you increased the amount of phosphorus that you saw in leachate, but when you tilled it in, you had less than when you left it on the surface. And this is recently applied, but this shows, again, from an environmental standpoint, that tillage isn't necessarily a bad thing. Okay, I'm going to finish up with just a couple of slides right here, and I wanted to get at the injection side of things. I work primarily with manure and less with mineral fertilizers, but there are studies also looking at mineral fertilizer application, and Mark talked a bit about that. So we've done work with a tool that injects poultry litter, so dry manure, into the ground, and we had some data from the first couple of years of our study on the eastern shore of Maryland that were pretty profound, where we just looked at corn yield. These were very high testing soils. They already had a lot of phosphorus in them. So we had one treatment where we didn't apply any litter, and then we broadcast the litter on the soil, so it's sitting on the surface, and you can see a little bump that actually statistically was not a significant bump when we broadcast it on the surface. But when we put it in the subsurface, so we're putting it down where the roots grow, we had a significant increase in yield. We haven't seen this everywhere, but at this particular site, we saw it multiple years. Here's the following year, so that was 2008, 2009. Again, we had yield benefit from the subsurface application. And so there are agronomic reasons for putting fertilizers and manures down below the soil surface where the crop roots can get to them, as well as environmental reasons. And I hope that the two presentations that you saw today have kind of convinced you of that. So let me kind of finish up here. Vertical stratification is kind of the Specter, and it's particularly a Specter if you're just ignorant about whether or not it exists in your soils. And so how do you know if it exists? You've got to try to assess it. That doesn't mean that you're telling people to go out all the time and measuring what's on the surface versus what they're getting in a deeper sample. But it does mean that periodically that needs to be done, or you could target it to areas where you're particularly concerned. And so soil sampling, I think, is probably the leading tool for addressing vertical stratification. Does it exist in the soil? Do I really need to be worried about it in my field? I would therefore be recommending that this be done regularly. It's hard enough in some areas to get farmers to go out and soil test regularly. I understand that. But while they're doing it, get them to basically convince themselves that vertical stratification either exists or doesn't exist in the field by taking a shallow sample, and that'd be a 2-inch sample as opposed to their regular agronomic sample. So then from the management standpoint, what you heard from myself and from Mark today is basically that water washes things off the surface and roots grow down. And so you want to do things that help to get phosphorus down into the soil and keep it off the surface. And so there are different ways of placing fertilizers so that you can incorporate them and put them where the roots are. But you also need to be considerate of factors affecting the application too. So I think that's it. This is my email if anybody wants to email me, and I look forward to taking any questions. And that's it.
Okay, thank you, Pete. Both of you have done a wonderful job. And I think we are fortunate to have all this valuable information available to us today. We do have some time for Q&A. Please enter your questions into the question box on your screen. I do have a couple to get us going. So I guess this could be for either Pete or Mark, but we've had a lot of questions on cover crops. So do cover crops help move the surface concentration lower into the soil profile, or just the opposite and add to stratification problems by plant decomposition? So either...
I'm happy to take that. Yeah, okay. Sorry, I didn't want to just take away from Mark if you want.
No, that's okay.
So it's an excellent question, and I'm always mindful when I show some data that show trade-offs related to cover crops. First and foremost, cover crops have tremendous benefit from the standpoint of capturing nutrients like nitrogen. They hold soil in place, and so in places where soil erosion is a concern, they have a tremendous benefit there. In the long term, they contribute to tilth, what's now called soil health, and they can help to improve infiltration through their contribution of organic matter. They're cover crops that actually introduce large macropores, so things like tillage radishes can really help with that. And so they are definitely a tool that needs to be included in any kind of watershed management strategy. Now, they they have large channels that they create, like a tillage radish, they can certainly help to work a fertilizer down into the ground. And that may or may not be a desired effect. If you're over a tile drain, there's the potential that you actually introduce a macropore that's helping to route things. But they certainly can be managed in a way that helps with the vertical stratification, but they're not going to prevent it. You're still looking at applying to the soil surface, and they're just not going to wash all of that down into the ground. So they have to be combined with something like injection, so that your application isn't to the top, but it's actually to the subsoil.
Okay, we have another question. Somebody was wondering if either of you could comment on the influence of mycorrhizal fungi on mitigating the loss of phosphorus in the top layer of the soil. Or has anyone done work on this?
You want me to get that, Mark, or?
Yeah, go ahead. I haven't done any work necessarily.
Okay, yeah. So vertical stratification is something that's been known for a long, long time. This is not a new issue, just like a lot of the dissolved phosphorus concentration issues that we're talking about here are not new, but they're new to us from a management standpoint. And so how is it that we address it? And so the mycorrhizal kind of question is interesting. They certainly can help to liberate and make plants available phosphorus that's in the soil that the plants may not get to, or that the roots may not get to. They provide tremendous. They help to extend the zone of soil that contributes to the root. But I'm not aware of anyone really working with them in a way to really tackle the vertical stratification part of things, to make the surface phosphorus more available to the roots. And that seems to me to be an open and excellent research question.
Okay, we have another question. Would you recommend rotational tillage with a cover crop in the tillage year to prevent erosion?
I mean, I think that is a good strategy. It's still applying. It comes down to application of the fertilizer. So if you're still tilling it in, you're going to get that erosion that first year, kind of like Pete showed. But if you do have the cover crops, that will help reduce your phosphorus losses by holding that sediment in place, and getting the fertilizer in the subsurface is where it needs to be. It doesn't need to be necessarily sitting on the surface. So, I mean, it comes back to what is your management style, and how comfortable you are with doing the tillage, or if you've been a no-till for a long time and what you view the benefits of it as. So I think what Pete and I have kind of both been saying is that there's a lot of different ways to avoid stratification, but once you have the stratification and once you have a buildup of phosphorus in the soil, it takes a long time for that phosphorus to leave the profile. It sits there for a long time and can create water quality problems for a long time.
Okay, and so I think this will be our final question. Let's see. You stated that P injection or phosphorus injection or tillage could reduce phosphorus losses up to 70% or so. How would you tell a diehard no-tiller that he needs to disturb his soil that hasn't been turned in 20 years?
Do you want to take that one, Mark? This is I get into trouble all the time in this area. First, no-till has tremendous benefits. So there's kind of two areas there. One of them is, are you going to inject it into the soil? And a lot of our injectors are using the same kind of implements that you see on a drill or on a planter. And so if you're paying attention to disturbance, we've done plenty of studies showing with injection that you can keep residue down and disturbance down to less than 20%, and that you can protect a good amount of the soil because you're not fully tilling, you're injecting right there. And so I think injection for a no-tiller is something that they just have to do, that they have to understand the node system is totally optimized, and that vertical stratification is a very real thing, and if they don't believe it, they should just go out and measure it. And that was the primary point that I made there. On the tillage end of things, I would say if you're a no-tiller and you went out and you saw that, say, you had very high concentration, say over 100 or 200 in your upper 2 inches, I'd question your long-term strategy then. It's not an easy thing to address. There are tremendous benefits from no-till, but it's not a panacea, and it has been oversold by those who have wandered into the water quality arena with no data and primarily with aspiration.
Yeah, I think you think about it in terms of balance. So we're trying to balance two different types. I mean, they're both phosphorus, particulate phosphorus and dissolved phosphorus. So they're the same nutrient, but they behave very differently. So if we, in 100% no-till, we're doing a really good job of reducing the particulate. If you were doing conventional moldboard plowing, you'd probably be doing a pretty good job managing your dissolve. But if you can do practices that kind of combine both, so you can optimize losses for particulate and optimize losses for dissolve, that's where we kind of need to be, I think, to solve these problems in Lake Erie.
Okay, well, in the interest of time, I'd like to wrap up the Q&A. I want to thank both Dr. Kleinman and Dr. Williams for joining us today. Really fantastic information that they have both shared.
Thank you.
Let's see. At this time, I want to recognize our participating ag retailers. If you are an ag retailer in the Great Lakes Basin that is interested in participating in this partnership to benefit your business and water quality, please contact me. Finally, I'd like to acknowledge our funders and collaborators that made this webinar possible, in particular, the support of the Great Lakes Protection Fund and the National Fish and Wildlife Foundation. So as we wrap up, please remember to look for the email later this afternoon with a webinar evaluation, webinar recording, PARM Ag Retailer Products and Services Survey, and a link to submit your CCA credentials to earn the 1.5 CCA CEUs. I want to thank you all again for joining us today, and I hope you join us again on February 22nd for our webinar on cover crop termination.